Everyone, my name is Konrad Witaszczyk. I'm a research associate and a first-year PhD student at the computer lab across the street. Today, I would like to talk about CHERI memory safety, in particular the software stack and ecosystem around the CHERI project. Before I get to the CHERI project itself, here is a list of references I will refer to. So once the presentation is shared, you can read more about things I will mention. Before also I get to the CHERI project, I would like to give you a bit of background why this project is interesting in particular and what kind of issues we want to solve. In 2020, Google analyzed vulnerabilities in their products in Chromium projects, and they discovered that around 70% of them are related to memory safety issues. 2 years before that, Microsoft did a similar analysis of their products, and surprisingly, they also discovered that around 70% of vulnerabilities in Microsoft products are also related to memory safety issues. In particular, spatial and temporal memory safety issues were the most common ones, including buffer overflows and use after free bugs. The CHERI project aims to mitigate such vulnerabilities through 2 mechanisms. First of all, fine-grained memory protection that can prevent buffer overflow and arbitrary code execution attacks, and that's the part I will be talking about. And secondly, scalable compartmentalisation that can prevent currently unknown or future vulnerabilities in the code. And that's the part my colleague Dapeng will talk about after me. CHERI was started by the University of Cambridge and SRI International in 2010. In 2014, ARM joined the collaboration, which led to an announcement in 2019 that the first hardware implementation of CHERI called ARM Morello will be developed. Last year, in January in 2022, the first Morello boards were shipped to various institutions. Initially, research was supported by DARPA, but later Morello and the SBD initiative I will briefly mention later were sponsored by UKRI and industry. In total, around £200 million were given to the DSPD initiative. In general, CHERI does not aim to replace existing CPUs, but extend them with new security primitives. It composes a capability system model with hardware and software and introduces a CHERI capability abstraction that extends the pointer abstraction with additional properties. In a pointer, on a 64-bit architecture, we have a 64-bit virtual address that references some place in memory. A CHERI capability extends this abstraction with a tag that protects a capability from being manipulated by an attacker, bounds that express what kind of regional memory can a capability reference, for example, an element in an array that can be used to iterate over the array. Permissions that express what kind of operation can be done with a capability, whether we can read or write or execute something from memory. And sealing that can be used to implement a non-monotonic transition between program parts that we call compartments. In 2021, the Capabilities Limited company analyzed how easy it would be to adapt an open source GUI stack to CHERI and Morello. They managed to compile 6 million lines of C and C++ code to achieve CHERI memory safety. And they discovered that under 0.03% of these lines of code needed to be modified to use CHERI capabilities everywhere to access memory. They also discovered that over 70% of vulnerabilities that had existed before would be mitigated if that code was compiled for CHERI at the time they were disclosed. As of today, we have a full hardware software stack consisting of obviously hardware, ARM Morello, but also emulators, compilers, debuggers, operating systems, but most importantly, and that's the part I was involved in, around 9,000 third-party software packages compiled for CHERI that only use capabilities to access memory. We also have around 23,000 third-party software that hasn't been adapted to CHERI yet, but is crucial to our end users, for example, Chrome and Firefox. Here you can see a picture of my desk at the computer lab across the street. It shows a CHERI BSD operating system kernel with drivers running a GUI environment consisting of KDE and Wayland and some basic applications. The whole software stack here uses capabilities to access memory. In fact, this software stack can be easily installed with a single terminal command using our package manager. Besides engineering and research efforts, there is a growing ecosystem around CHERI. The DSBD initiative, funded by UKRI and industry, as I mentioned before, consists of multiple government and academic institutions and companies that collaborate with each other on CHERI-related projects. DSBD also runs a technology access program for UK-based companies that can experiment with Morello and create prototypes on the actual hardware. We currently collaborate with around 30 companies that I meet on a regular basis. Several of them already discovered that using Morello and CHERI, they discovered vulnerabilities in their code, but also they analyzed past vulnerabilities using CHERI. If you would like to apply for this program, or if you know someone who could apply, here is a link to the TAP cohort 4 call that is open now. Just go to dsb.tech. There are also some leaflets on the program in front of me. If you would like to talk to us or just follow research, you can join the CHERI CPU Slack or mailing lists. Go to cheri-cpu.org and you can find around 300 people following CHERI there. Thank you.